Okay, so the next thing we're going to talk about, this is the Section 4 labs that are blockchain programming languages and Vyper. So the first thing I want to start with is the difference between Turing completeness and non-Turing completeness. And you might have heard of Turing and Turing tests. This is not what that means. So here's an article how people don't even know what a Turing is. Well, I mean, legitimately, they don't know what a Turing test is. So this Dilbert is hilarious because the people who fail it compared to you are high achievers. As ultimate throwing shade at his boss. And so Turing completeness has nothing to do with that Turing test. There is a really good article that talks about whether or not smart contracts need this property of Turing completeness. So what is this property? The first thing is the definition of a Turing machine. This is a machine that, if given an infinite amount of RAM, and that can run an infinite amount of time, it can run a finite program that is basically reading and writing that memory, and it can also dictate when to terminate itself. So this is the machine, and if you have a Turing machine like this, then the definition of Turing completeness is that you have the ability to implement any computable function on this machine. You have the ability to write a function that won't terminate, so an infinite loop, so the halting problem that comes out of this. And it has the ability to use an infinite amount of memory. And then the question is does this sound like something a smart contract actually needs? And so a lot of people are saying no. Then why do we have Solidity? Solidity is a Turing-complete programming language. You can write infinite loops in it. You can do all of these sorts of computations if given enough gas. But you're not given an infinite amount of gas. So then immediately it comes to question whether or not you need this style of programming language. And so here's a meme about the Swiss including everything in their Swiss Army knife. And so one is like, why did they include this thing? And so they imagine maybe it's because they were confident in their chances of victory. Okay, so non-Turing completeness. If you have a language that does not support loops, does not support recursion, eliminates any kind of go-to statement, that are go-to constructs that aren't guaranteed to terminate. Because when you do a go-to, that thing could actually implement an infinite loop. So you have to get rid of that in your language. And then any kind of construct that prevents analysis of the underlying program. And then a non-Turing complete machine will have finite computational and memory resources. So this is the style of operation that people are suggesting is a more appropriate way of programming a smart contract. So they did a study earlier this year, and this actually came out of that article. I think that article is the same as the one I had earlier. Yeah, it's the same article. They did an analysis of all of the smart contracts on Ethereum, and they checked to see whether or not these smart contracts needed to use loops or needed to use recursion. And they looked at this, and the vast majority, this is the large part, this dark part, didn't need any of the Turing complete characteristics. So for these contracts, you wouldn't need Solidity. You wouldn't need the full Turing completeness of Solidity. So a very tiny percent used while loops, a very tiny percent used recursion, a quarter of them use for loops. But a lot of these for loops are bounded. They know exactly the upper limit of the for loop, which makes it a deterministic loop, is the idea. Okay, and so this is a quote from Buterin. He says it's not that big of a limitation. There are very few contract examples where they actually have needed this facility. Okay, so this motivates Vyper. It's a non-Turing complete Pythonic programming language. So the syntax is based on Python. The language and the compiler are much simpler, although eye of the beholder, as Ben has been finding out, that's Maybe not as, well, I would say the language is nice, but the tooling around the language is really horrible. Sorry. What Vyper does is it limits the functionality that's built into the programming language that cause a lot of the vulnerabilities you have just gone through in the previous 3 weeks of this class. The programming language is trying to give you models that are very simple, and this allows humans to be able to audit the code easily. Like, it should be human understandable from the get-go, which is basically Python's claim to fame, right? This is why they choose Python as a base syntax here. And it makes it maximally difficult to have misleading code, to do some code obfuscation. And then, of course, because you want to run it on Ethereum, this will eventually compile down to EVM bytecode. So even though the bytecode, the virtual machine, is Turing complete, your subset of bytecode that you're generating is not going to be. Okay, so here are some links. A link to the interpreter, the online interpreter, the project page, and then a whole bunch of example contracts written in Vyper. Are all these 3 links. Okay, so how does it do this? Well, the first thing is that, first class of things that it does is it tries to get rid of all the complexity from Solidity. The first thing it does is it removes modifiers. It says if you want to have some code as a gatekeeper for executing this function, you have to write it out. Be explicit everywhere. So yeah, the code might be a little longer, but the problem with doing a modifier is that the code that implements that modifier is in some other file. And then, in order for you to understand the code you're reading, you have to go back and forth between multiple files. And so, like for your Solidity, the CTF levels, you have to like go back and forth between base contracts, between the framework, the modifier. You're like, what is that modifier? Is manager? How is that implemented? And all of a sudden, you're going back and forth between code. So they want to get rid of that. It removes class inheritance. So it's like this, and we saw a bunch of inheriting contracts that caused complexity that forced us to inject security vulnerabilities in there. So this is similar in that you have to access multiple files to figure out what the inheritance results in. And moreover, whenever you have conflicts in the things that you're inheriting, so if you have a base contract that inherits from a derived contract that's derived from 2 base contracts, and those base contracts have a conflicting method, then which one do you call? And this is why they decide to get rid of inheritance in this language. It removes inline assembly, and the reason why you remove inline assembly, if you're trying to analyze all of the parts of your code that access a single variable, like the balance of the user, if someone has embedded inline assembly, you can use that assembly to inject an alias, a memory alias that modifies that piece of that variable that you're really interested in validating the properties for. So memory aliasing is, and actually if you remember 201, memory aliasing is really difficult for a compiler to deal with, and it's really difficult for program analysis. So they get rid of this embedded assembly so that they have very precise guarantees on what is modifying which variables. It removes function overloading. So we saw that in the CTF level. You can't use the same name for 2 different function parameter sets. So this gets rid of that confusion. And then it removes operator overloading for the exact same reason. So this keeps all of this complexity and obfuscation is now removed from the language. It also has a set of features that remove vulnerable patterns. So it gets rid of infinite and arbitrary length loops. These things are hard to analyze because the gas estimation has no idea what the runtime is on a loop that has a condition that is a dynamic one, a runtime condition. And if you recall that the contract that had on delete had a loop to run, it gets rid of that because then you don't have this unbounded execution time in your contracts. It removes recursive calling, so you cannot implement a reentrant attack a reentrancy attack on this thing. All of the integers are 256 bits. So again, that obfuscation between the 8-bit, the 16, the 32, that's removed. And then here are some syntax differences. Instead of address this or address 0, you can just use the self keyword because this is how Python does it, to refer to itself. The 0 address, and then instead of the require keyword in Solidity, these things are written as asserts in Vyper. Other features, strongly and statically typed, as you would expect for a programming language that you want to secure stuff with. And I think you've probably been beaten over the head with the typing in this, at least in this CS department, of how important strongly and statically typed languages are. Bounds and overflow checking on array accesses. So if you've taken 201, you realize the importance of making sure out-of-bound memory reads aren't possible. Overflow and underflow checks for arithmetic operations. You don't want to have to import safe math on every single smart contract and completely avoid the built-in add and subtract operators. So it's like, that's a waste of syntax. It's sort of like JavaScript blowing away the double equals. Like double equals is completely useless in JavaScript. It's like, yeah, well, plus, minus, times, and div, that's completely useless in Solidity. But so Vyper gives you that back again, which is a nice thing. It actually implements decimal fixed point numbers. So if you recall from Solidity, it's all integers. And so a lot of people are like, yeah, I want to actually have a real number system. And that's what Vyper will implement for you. And then the biggest thing is precise upper bounds on gas consumption. So the non-Turing completeness is what you would really want to use Vyper for. Okay, so I'm going to briefly go over the language syntax for Vyper. Because it's Pythonic, some of this stuff we can just breeze through. The first thing is a way to declare variables. This is slightly different than what you would get in Python because Python is dynamically typed. And so in order to, there are some efforts, like Instagram has this static sort of thing around Python, static type checking infrastructure around Python. This is the same thing, but done in Vyper. You are specifying the data type for every variable that you then use in the smart contract. So that's basically what this is. Here is a state variable that, a variable named myStateVariable that you want to declare as a signed 128-bit integer. So you give it the variable name first, and then after the colon, you specify its type. So this is the same thing as a Boolean. So you're declaring that variable as a Boolean. These are declarations for two variables as unsigned ints and signed ints of particular widths. Here is your decimal fixed point type as a decimal keyword. Here's how you declare an address, a variable that's an address, a 20-byte Ethereum address. And then one of the interesting things about the address is that it has member functions that are built in. So if you have an address and you say address.balance, that returns the amount of way associated with that address. If you have address.codesize, this is the same thing to figure out whether or not that address has some, I guess that was the one level you just did, the scratch card one, whether or not there's code associated with it. And the same thing is contract, which I think does something similar. It has these unit types, and this is actually in Solidity, where you can specify timestamps and their units as seconds, minutes, years, days. And then it also has this unit type called way value, which is the amount of ether given in way. And you'll see these things being used throughout the code that we'll walk through. It has strings, just like Python. It has byte arrays that are similar to Solidity's, where you have a byte array hash that you say is a bytes 32. And this is basically the same size as a uint, except you can index this hash using array notation, just like Solidity. It implements lists. So these are fixed size arrays of elements of a specified type. So here is a list of integers being declared, 3-integer array, where you can set the integers to particular values, and then you can index the array. And it also has the same thing that Solidity has with mappings. So these are your dictionaries, basically. So you declare a dictionary or a map that has a key of an address and then has the value of a decimal. And then this thing will set the key of message sender to one way. You have structured data types. So this is how you declare a struct called bid. And you say the attributes are an ID that's a uint and a deposit that's some value in way. And then here's how you would instantiate that structure. So here's an instance of it. And then here's where you declare an instance of it and then initialize the attributes in it. And then here's how you would access it to set the deposit value to a particular value. Okay, so this kind of stuff should, I mean, it's slightly different than what you're used to, but it should make sense how the syntax works. Okay, the operators, they're all similar to Python and Solidity. They've got the traditional comparison, the bitwise operators. Well, actually, no. The bitwise operators are done as function calls, but all the arithmetic and the logical ones are similar to your other languages. There are some built-in functions. These are just a select number of them. The send function is built in to send a recipient some amount away, and this is equivalent to the transfer in Solidity. You can clear a data type, you can return the length of a variable, you can get min and max and floor and ceiling of all the numbers that are associated with this language. And I should say, this is a completely moving target. So Solidity was a moving target, and it still is, but this thing is really, this is really bleeding edge. The Vyper stuff. Within the last year or so, they've made a ton of these. Within the last year, they've made it so that we could maybe use it. So that's why we're gonna give it a go. But yeah, what's it? Yeah, I always want to hedge because yeah, the very first time I run anything, I'm like, okay, better lower expectations, but. There are, I mean, I was looking at the docs, and there are some legitimately complex contracts that are written and that do compile and work. And I was able to get my simple contracts to compile and work. And so I think we can do, and I'm not asking you to build like an ERC20 implementation in Vyper. We're doing for your final, you're going to do your final project, well, one of the options for your final project is to do a smart contract in Vyper. So we'll have to, I will interact with you if you run into issues with Vyper, and then we can see about alternatives. Yeah. Okay, so defining your functions, this is very Pythonic, using the def keyword. Here's an example of using the assert. This is similar to the require. And then the return is different. Well, this is something that people are adopting, the arrow operator to specify the return values on the function declaration. And then all you do is you specify the type of the data that you're returning. And so in this case, I'm going to return the away value, which is the self.balance. Okay. Just like in Solidity, there are visibility declarations, and Vyper did the right thing. Its default setting on everything is private, which is what, yeah, default off should be the thing. You have to explicitly denote all the things that you want public. By wrapping it with this public syntax. So in this case, I want this particular mapping to be viewable publicly from an external call. So this is the declaration for this. And then you explicitly denote public functions, ones that are externally callable, using the decorator syntax. And the decorator syntax I describe in one of these Python screencasts. This tells you these are wrappers to associate function calls that are wrapped around other function calls. So this wraps the public function call around withdraw and allows everybody to be able to call the withdraw function. All right. There are other function decorators like payable to specify that that particular method can accept payment. Non-reentrant is a keyword, and then constant is similar to view, where it's not going to change anything on the blockchain. So these are just syntactical modifiers. So here, and the last one is the default function. So this is the way you specify the fallback function. So in Solidity, it was just an unnamed function. Here, it's using the Pythonic __ label __, and in this case, it's called the default function. And then this is the function that gets called whenever you have a function call that is not known to the smart contract. You'll call the fallback, and then if you're getting sent money, you'll call the fallback. The constructor function uses Pythonic syntax, so __ init __ in Python is the constructor. And so in this case, you have these attributes for your contract, and then they all get set, as we've done previously, they all get set in the constructor. These are the parameters that you would instantiate the contract with, and then you just go ahead and update these attributes in the constructor. The questions about any of this? Or does this look reasonably familiar to you? Okay. Control flow. This is definitely Pythonic, the if-else and the for loops. And typically you would want this to be bounded, these for loops to be bounded in their range. And that's why they're there. And then events, this is to send stuff to the web browser. This is the events interface, which I'm not going to cover. Okay, so there are some, so this is not in a state that I could have you do. This is like they're trying to be the equivalent of crypto zombies for Vyper, but I couldn't get this thing to work. So I don't know if it works now, but if you want to check again. I just checked last month, and it didn't work, but maybe your luck is better than mine. So I ended up creating my own Vyper labs, which is what, let me see. Which I will go through now. So the first one is to take that my contract code from way back when and to compile and deploy a Vyper version of it on Ropsten. So you go into Remix. Remix has got a Vyper environment now. You go and then instead of Solidity, you click Vyper. And then this is the code that's the equivalent Vyper code for my contract. You can see it's got a constructor that's public that sets the owner to the sender. It's got a way of self-destructing this cash out function that basically returns all the money back to the owner. It's got a get balance that's public and it's constant because all it's doing is reading the balance of the contract and then returning the way value. And then the fallback function, which is just accepting money. It doesn't execute anything. So you copy and paste that thing into, you go into Remix, you go to the Vyper tab, which is over here. You click on Remote Compiler. You don't want the local one. You want the remote one. So, and then you interact with Remix to, you compile this and then you deploy it. And then I want you to interact with the smart contract by adding value to it, getting the balance, cashing out, and then doing the screenshot just like you did previously with the Solidity version. So that's a simple hello world of Vyper. Then what I want you to do is to do this underflow contract. So one of the things that Vyper does is it checks for arithmetic underflow. So I want you to show this, to see the kinds of errors that this smart contract will give when you're trying to do the same shenanigans that you did in the SI token sale one. Like, try and see if you can do that particular level on Vyper, and you shouldn't, because it's doing this. When you compile Vyper down to EVM bytecode, on all the arithmetic operations, you can see EVM bytecode that is checking the result before continuing. This is overhead. So the EVM bytecode for implementing all of these checks is pure overhead. So the gas, you'll be consuming a lot more gas on these arithmetic operations because you don't get this thing for free. You don't get underflow and overflow checking for free. It's checking on every add. But this is what the SafeMath library was doing already. SafeMath was already putting those checks in there. It was messing with your syntax to put the checks in. So what Vyper is doing is just taking the regular operators and then building the checks in band so that you don't have to see it syntactically. Okay. So this is the contract. You declare these variables, the owner, the instructor, which is me, because in this contract, I get the commission for anybody who trades, but you can set the commission to something really small. So it's the owner, which is you, the instructor, which is me, the commission that I take out on every transaction, and then the amount of funds that I have. So the constructor sets the sender to you, and this is my wallet address, the amount of funds, and then I get 1,000 Wei for any transaction here. And then here's a payable fallback function that adds the message value to the contract. And then implement cash out. But before you cash out this contract, you're going to send me some kind of commission, and then you're going to self-destruct the rest of the money back to yourself. And then there is this reduce commission call that allows you, if you call it, to subtract my commission by 500. And what I'm going to do is I'm going to try and hit that multiple times to make my commission a really large number. Or you can call it multiple times to try and get me to 0, but then like call it another time to see if you can get it to see if you can get the underflow to make my commission a large uint 256 is the idea. So I want you to deploy that contract and then start interacting with it to try and trigger the underflow and see what you get. What you should get is an assertion. So if you call this once, it should be fine. You call it again, it should be fine because it gives you 0. You call it a third time, and then what should happen is that the EVM bytecode sees the underflow, throws an assert, and then that contract, that thing should fail. It should not underflow that particular value. That's what I want you to see as part of this lab, that the check has been built in. And this is what you should be looking for if you're ever charged with creating a smart contract. You actually want that so that the programmer doesn't make this kind of error without knowing what's going on. Okay. Okay, so you compile and you deploy it, and then you interact with it. Okay. The second lab is just to re-implement fundraiser in Vyper. Just doing a translation of the fundraiser contract over to Vyper. Okay. So with that, the last thing I want to cover today, I have time. People have already asked about what this final project is going to be. So final projects, you have some options here. The first is a dApp of your own in Vyper. Any number of, so I gave you a link. There's a link that has a whole bunch of different smart contracts written in Vyper. You can look at that for ideas, and maybe you can derive from one of those contracts and build something on top of it. So games, auctions, a parking meter, stock market application, and these are fake applications, obviously, but any number of things. I just want you to be creative in what you implement. You can build your own CTF level in Vyper. Try and make a vulnerable contract in Vyper that we can all exploit, and put it up with some ETH, and then say, hey, instructor, try and subvert my contract, or actually submit the source code that we can deploy to try and subvert to get the money back out of. And you've seen enough levels in security innovations and the code for those levels to be able to say, hey, you know what? Can I re-implement scratch card or record label or any one of these other vulnerable contracts in Vyper? And you'll find that I can't do SI token sale in Vyper. I can't do trust fund in Vyper, right? And then this is the exercise that I would want you to do if you do a CTF level. The last one won't become apparent to you until after next week. I have in our last section of labs, we're going to be using Manticore to automatically exploit like 5 or 4 different CTF levels in the Security Innovation CTF. If you want, this is super advanced. You could try and see if you can use Manticore to solve one that we haven't gone through. And then if you do come up with that, I would ask the deliverable for this is a code lab that includes that's very similar to the ones that you'll be doing next week. That's similar to that. These are the instructions for using Manticore to solve that level. So a lot of different options. If you want to do something else outside of these 3 options, talk to me individually, and then maybe we can negotiate. All right. So are there any questions about what I'm expecting out of this? The deliverables are source code in your repo in a directory called Final, and then what I'm going to have you do is submit a screencast walkthrough of the source code and a demo of its use. And then this will be submitted to a MediaSpace channel that I'm going to create and then add you as contributors to. It's going to be a 20-minute maximum on the screencast. And then you'll basically walk through all the parts of the code that you've written. I am allowing people to pair up on the project. And if you do a project in pairs, then in your screencast, the part of the code that a particular student has implemented, that has to be narrated by that student. So that's how I'll assign sort of the work between the 2 partners of a project. Okay, so that is it. Are there questions? Yeah, it'll be the end of finals week, like a Saturday, probably. Okay. I'm shooting for that Saturday, I think, is what I'll do. Is that the 7th or the 14th? I can't remember what day that is. The 14th, yeah. Okay. That'll give, because I know the end of finals week is probably where people have more time. So I'll push that to the end. All right, that's all I have.